Welcome back, students. So what we had been discussing in last lecture, we had been discussing about bottom-up parsers. We had started discussing that bottom-up parsers are subdivided into two categories: operator precedence parser and shift reduce parsers. We have started discussing with the basic shift reduce parser, and we had seen the difficulty that if you directly, so this is the category we have already discussed, and then we had discussed that if you directly apply shift reduce parser, you will end up having difficulty because you are taking manual decision, hence multiple times you have to perform backtracking, you have to go back, roll back all the actions you have performed. That is wastage of efforts and time. So we had concluded over a method, and that method said that whenever you have to apply bottom up parser, shift reduce parser, what you need to do is first of all apply top down parser with rightmost derivation and then follow the actions which you have performed in reverse. So we had been solving the same example we did wrongly previously, but the first step that we had to apply was apply top down method, top down parsing with rightmost derivation, which we had done in last lecture. So we are going to move ahead again with the example like we did earlier. In shift reduce parser, what we need to do is the expression is terminated by dollar and the bottom of the stack will also contain dollar. But we are not going to push the start symbol, because what we are going to do over here is applying reduction will try to reach to the start symbol. Okay. So when the stack is initially empty, the first operation by default that you have to perform is shift. So what I will have over here, dollar ID multiplication ID minus ID dollar as it is. Now observe the actions that you have to perform in rightmost derivation but in reverse. What is the first action that you have to perform? That is ID should be reduced to F. ID should be reduced to F. So actions we are performing are reverse, so that the right hand side is going to be replaced by the left hand side, not terminal. So ID should be reduced to F. Now which ID? If you observe over here, that is the ID which is on left side of multiplication, which we have right now in the stack. Right? Are you getting this? The first occurrence of ID which we have pushed onto the stack is the same ID over here which we need to reduce to F. So the action that you have to perform over here is ID need to be reduced to F. So what we are going to do, ID will be popped, F will be pushed, the remaining expression will remain as it is. Okay. What is the next action that you have to perform over here? The same F need to be converted to T. If you observe, the same F need to be converted to T. The same F which is there in the stack. So the action is F need to be reduced to T. So F will be popped and T will be pushed. Multiplication ID minus ID dollar will be as it is in the expression. What is the third rule that need to be applied? Again ID need to be reduced to F. Now do you have ID in the stack? No. What it means? It means that you need to bring ID to the stack to perform the third action. Now it means you have to perform a shift operation. So if you perform a shift operation, the first input symbol that you get is multiplication. The remaining expression is ID minus ID dollar. Yet you don't have ID on top of the stack. So once again what you have to do is perform a shift operation. So what you have over here, T multiplied with ID minus ID dollar will be there in the expression. Now you have ID on top of the stack. So this third action can be performed. If you observe over here, that is incidentally the same ID which is going to be converted to F, the ID which is on the right hand side of F, the ID which is on the right hand side of the F, that is going to be converted to F, but that is multiplication, that is going to be converted to F. So what you are going to do, ID will be reduced to F. So what will happen over here, ID will be popped, F will be pushed, minus ID dollar will be as it is. Okay. What is the next action that need to be performed? T multiplied by F should be reduced to T. So observe, do you have the top of the stack frame that contains T multiplied by F? Yes, we have. So what we have to do? We have to perform T multiplied by F should be reduced to T. So entirely T multiplied by F will be popped and T will be pushed. Minus ID dollar will remain as it is. Now what is the next action that you have to perform? Observe. The next action says T should be reduced to E. Which T? the t which is there on left hand side of minus, right? That is incidentally the same t we have over here onto the stack. So the action that you have to perform is t should be reduced to e. So I'll pop t and e will be pushed. Minus id dollar will remain as it is, right? What is the next action that you have to perform? Once again, id need to be reduced to f. So we have to bring the id to stack for performing reduction. E will be as it is. One shift will be performed. So minus will be there onto the stack. A shift is performed. Okay. Now once again a shift operation is going to be performed. Once again a shift. So that will bring E minus ID onto the top of the stack. Right. Now on top of the stack what you have? ID. So the next operation, sixth operation can be applied. Which ID is going to be reduced to F? The ID which is on right hand side of minus. Which is on right hand side of minus. Exactly same. So what action I am going to perform? ID will be reduced to F. So dollar E minus F. Okay. Now what is the next action that you have to perform? Seventh action. F should be reduced to T. F should be reduced to T. Which F? So F which is on right hand side of minus, that should be reduced to T. Okay. So that is on top of the stack incidentally. So F will be popped and T will be pushed. Dollar. Okay. What is the next action that you are going to perform? Entirely E minus T should be popped and E should be pushed. So that is the action we are going to perform. So E minus T, the substring will be popped and E is going to be pushed. Dollar. Right. So as we have reached to the start symbol of the grammar successfully, we will declare success, and this expression we have written over here is syntactically correct. Are you getting this? So this is how we are checking whether the given expression is syntactically correct or not. So this is all about shift reduce parser that you need to know. So in example, they can ask you a question like explain shift reduce parser in detail with example. So you need to state two actions shift and reduce, and then you need to explain with a sample example. Now there are two terms which are very important over here, and these terms are handle and handle pruning. So let me explain these two terms. Many times in GTU paper they have asked this question, define handle or define handle pruning, or explain shift reduce parser in detail with handle and handle pruning. Okay. So if we revisit this example, then what actions we are performing over here is, for example, at this particular instance, in this particular stack frame, what you are doing? ID over here which is on top of the stack is going to be reduced to F. Why? Because there is one rule where ID is on right hand side, and if you reduce that ID to F, you are following the reverse of rightmost derivation. Let me repeat that a symbol or a substring on top of the stack, when you try to replace by left hand side non-terminal such that you are following reverse of rightmost derivation, then that symbol or substring is called handle. Handle is something you are replacing by left hand side non-terminal. So for this particular frame, ID is handle. But if I am talking about this particular frame, then entire T multiplied by F is going to be replaced by capital T. So what is going to be handle in this frame? T multiplied by F. Why? Let me repeat. When the substring or symbol which is on top of the stack matches with any of the production's right hand side, so when you replace that substring or symbol with left hand side non-terminal, you are following the reverse of rightmost derivation successfully, then that substring or symbol which is on top of the stack is called handle. It is called handle. And replacing that substring or symbol which is on top of the stack by the left hand side non-terminal, this process of replacement is called handle pruning. Let me differentiate what is handle and what is handle pruning. So if again I am talking about this particular frame, then the symbol or substring which is on top of the stack, if it matches with the right hand side of any production, such that if you replace it by the left hand side non-terminal, you are following the reverse of rightmost derivation, then that symbol or substring is called handle, and replacing it by the left hand side non-terminal, that process is called handle pruning, right? So handle will be different at different steps. For example, if we are talking about this step, then entire E minus T is going to be handle, because and replacing E minus T with the non-terminal E, this process is called handle pruning. So this is all about a shift reduce parser, and now we are a lot clear with what handle means and what handle pruning means. So handle is always going to be on top of the stack, whether it is a single symbol or it is substring of the different symbols, multiple symbols, it is always on top of the stack. And when you replace handle by the left hand side non-terminal in the productions, you will be successfully following the reverse of rightmost derivation, and the entire process is going to, of replacement will be called handle pruning, right? So this is all about shift reduce parser that we need to know. We are going to move to the next parser, which is called operator precedence parser. Okay, operator precedence parser. So basically we are going to discuss two algorithms with operator precedence parser, the basic algorithm of parsing the expressions, and then an algorithm where we are going to use the graphs and numbers for enforcing the concept of precedence. So we'll start with the basic concept in operator precedence parsing. The question that has been asked many a times in Vivas, GTU exams and GATE exam is whether the given grammar is a valid operator precedence grammar or not, or when you can say a grammar is valid operator precedence, pardon, I won't be writing the full name, valid operator precedence grammar. So there are two conditions that a grammar need to follow for being operator precedence grammar. What is the first condition? A grammar should never have any production which derives epsilon. A grammar should never have any production where any non-terminal is deriving epsilon. This is not allowed. Even if a single non-terminal is deriving epsilon, that grammar won't be a valid operator precedence grammar. What is the second condition? Second condition says two consecutive non-terminals are not allowed. Two consecutive non-terminals are not allowed. So if I write a rule like A derives X, Y, small z, if my grammar has even a single production like A derives X, Y, Z, this makes my grammar not a valid operator precedence grammar. Why? Because there are two non-terminal which appears consecutively over here. Let us understand two conditions with examples. So if suppose I have a grammar like this, E derives E, B, E or ID, where B derives plus, minus, equal to. And if I'll ask you a question that whether the given grammar is a valid operator precedence grammar or not, what will be the answer? Answer is no. It is not a valid operator precedence grammar. Why? Because if you observe over here in the first rule, you have capital E, capital B, capital F. So consecutive non-terminals are present, and hence it violates the second condition. So this grammar is not valid operator precedence grammar. But if you observe the semantic of the grammar, this grammar can be converted to valid operator precedence grammar. How? If you replace capital B by the terminal it holds, then the grammar will be E derives E plus F, E minus F, or E equal to F or ID. Okay, so you can observe over here that none of the non-terminal is deriving over here. None of the non-terminal over here is deriving you. Sorry, this is E itself. This is not F, this is E. Okay, fine. So none of the non-terminal is deriving epsilon. So this condition is satisfied, and none of two consecutive non-terminals are also not there. So now this grammar is a valid operator precedence grammar. Are you getting this? Let us take one more example so it will be clear. Suppose you have a grammar which says S derives S, A, S or A, and A derives B, S, B or B, where S is the start symbol. The question is whether the given grammar is a valid operator precedence grammar or not. The answer is it is not a valid operator precedence grammar. Why? If you observe this, you have consecutive non-terminals that invalidates this grammar to be operator precedence grammar. Once again, this can be not all grammars which appears not to be operator precedence grammar can be converted to valid operator precedence grammar, but some can be. In this example, if you observe, this A can be replaced by small b or B as B. In any of the case, making the replacement will make your grammar a valid operator precedence grammar. So this can be written as S derives SB, SB, S. So this is where A comes, or A or SBS. Fine. So what we have done over here? S derives SAS. So A has been replaced by BSB. So now it is SBSBS. A has been written as it is. Okay. This won't be the case. Fine. So we can observe over here that two consecutive non-terminals are not there, and hence now it can be said a valid operator precedence grammar. Right? Okay. Fine. So fine. But still, see, the second replacement should also be done, and so third rule will be replace A by B. So SBS. So there are three rules will be resulted over here out of the two rules after replacing these two productions. And this grammar now will be valid operator precedence grammar because any of the production is not deriving epsilon and two consecutive non-terminals are also not there. So this is how we can check whether the given grammar is valid operator precedence grammar or not. Now we need to discuss that how we are going to apply operator precedence algorithm. For that we need to understand precedence relationship and how precedence operator is going to be applied. So like we have different operators, we have precedence operator also. Like we have greater than, less than, equal to operator, we are over here going to use an operator which we are going to call precedence operator, which will be written like this. So these three are mathematical operator and these three are precedence operator, and these are hypothetical operator which are not actually in existence, but we are going to use these operators for enforcing the precedence. So it is something like if I have a symbol theta1 and if I have a symbol theta2, when I write this greater than and between there is a dot, it indicates theta1 has higher precedence over theta2. When I write it like theta1 less than theta2 with a dot, it indicates theta1 has lesser precedence over theta2. When I write like this theta1 equal to theta2, it indicates that theta1 and theta2 both have the same precedence. Right? So this indicates precedence operator. Now we need to, first, before applying the algorithm, we need to understand the precedence between the basic operators, basic terminals which we are going to use, so that operator precedence parsing can be applied. So that we will be discussing in the next part of the same lecture. So keep watching. Thank you.